So our next speaker will be Carol Anne Clayson. Carol Anne is a scientist at Woods Hole Oceanographic Institution and the director of the Ocean and Climate Change Institute. Her talk today will focus on multi-scale processes and ocean atmosphere interaction in the tropical Pacific, and she has some compelling questions for you to consider at the end. So thank you, Carol Anne.
Thank you, Charlotte. You can hear me just fine. Okay. Yeah, Charlotte and Anish asked me to be a provocative in this talk, and that's not my natural milieu. So I'm going to do my best to do something that maybe can keep us moving forward in terms of thinking about multi-scale processes. So I want to start back with the Toga Core intensive observation period. So this was an experiment in 92, 93, and in some ways there were other experiments that went on in the tropical Pacific before this time, but this is one that was headlined by Peter Webster and Roger Lucas, so both an atmospheric scientist and an oceanographer, really putting this together to look at the ocean and atmosphere together. And I'm just going to highlight a few of the science goals that they had, which was looking at how are the ocean and atmosphere coupled, how is convection organized, what's the ocean response to buoyancy and wind stress forcing, what are the multi-scale interactions that extend to the ocean and atmospheric influence, and the ultimate objective of the core data set, as they said, is to improve air-sea interaction and boundary layer parameterizations in models of the ocean and the atmosphere and to validate coupled models. To some extent, these are really still some of our questions. Now, I don't want to disagree that we had many, many accomplishments, and these are just a few of the sample accomplishments that had to do with Flux, the development of the core Flux algorithm, a lot of understanding about the MJO, westerly wind bursts, convection and rainfall, improved ocean mixing models. So many, many accomplishments. So if we look at this is a schematic from the Webster and Lucas paper. So the setup in thinking of the Toga Core experiment was basically three components of a major field experiment, right? The atmospheric component, the oceanographic component, and the interface. And if you look, in fact, at the figure that they included, it's kind of interesting that they have the upper ocean separated out from the deep ocean, but the atmosphere is just one big box. But in any case, it's atmosphere, ocean, and the interface. And it was a major undertaking. Something like 1,200 people were involved, 16,000 ship hours, 125 aircraft flights, 12,000 radiosondes. So a major undertaking. But in the time since then, a few things have changed. Higher resolution space and timescales have become important, and the idea of the coupling between the ocean and the atmosphere has evolved. And I'll just touch on these briefly. And there have been a number of new types of observations and platforms which have become available. So my overall question here, is it worth discussing sort of the idea of a new Toga Core? So I'm just going to pull out a few quick examples. This one, in this case, the mesoscale coupling. This was a paper by Dudley Chilton that was looking in the tropical Eastern Pacific. On the top is the sea surface temperature, and on the bottom is the wind stress in color with the sea surface temperature overlaid. And what you can see when you look at this is that very close physical relationship in the structure between the sea surface temperature and the winds. And then this is a paper just a year later by Hashizumi, and where they took, now they're looking again in the same region, and they had aircraft flying across, you can see across the, from warm to cold to warm, across the sea surface temperature band. You can see the sea surface temperature here in the bottom figure. You can see it goes from warm to cold to warm. And now this is the boundary layer, atmospheric boundary layer measurements. And you can see again, the dropping of the boundary layer height, the expansion of the boundary layer height. So clearly a very close relationship between the sea surface temperature and the atmospheric boundary layer. So what we've found in the decades since Toga Core is that if you look sort of on the large scale and you do a correlation between the wind speed and the sea surface temperature, that generally you get everywhere a negative correlation here in blue, which means the ocean is basically just responding to the atmosphere. The atmosphere is forcing the ocean and the ocean is just responding. If you do a high pass filter of the same data, so you're looking now at say 100 to 1,000 kilometer scales, that correlation actually changes sign. and you get an oceanic forcing of the atmosphere on frontal and mesoscales. And this is from a paper by WHOI. And so, you know, the whole idea of how this coupling is playing out and on what scales has really changed. One other quick example are, you know, cold pools, for instance, on the atmospheric side have become of real interest. These are convectively produced. They span 10 to 200 kilometers in diameter and last typically for less than a day. They have an impact on convection. This is a paper from Paquita and company, and you can see sort of on the curve here, this circle of convection at the edge of the cold pool. And there are a lot of questions about their impact on convection. Do they help to facilitate transitions from high to low albedo, shallow cloud cover? How about the transitions from shallow to deep convection? Does that affect the eastward propagation of MJO? So, you know, there's a lot of questions of responses to this. And this is a paper by Simon Dezoka where they're using about 215 cold pool events in Dynamo. And you can just see, first of all, this change in air temperature, the decrease, changes in humidity, wind impact, and then a sea surface temperature. And some more recent papers have looked at, you know, the coupling of that impact of the cold pool on the upper ocean in SST and the relationships with freshwater fluxes, but we really don't have yet even a feedback sort of mechanism working and understanding of this one. In addition to horizontal resolution, the vertical resolution that we're looking at and running our models at also matters. So this is results from Eric Skillingstad and a project we're doing for TPOS. So here he's running a coupled wharf-ROMS model where it's a triply nested wharf with the inner resolution, the horizontal resolution at 4 kilometers. And on the left is running ROMS with a 1 meter vertical resolution, and on the right is running ROMS with a 5 meter vertical resolution. And you can just see the sea surface temperature. You just see that diurnal warming is much more visible in a higher resolution, because in this case, you're essentially keeping the solar radiation where it's being absorbed near the surface than in the 5 meter resolution where it's getting mixed out and placed into a much deeper column of water. And this is from the same simulation, but this is now the sea surface salinity. Again, the high resolution on the left and the lower resolution ocean on the right. And you can just see in that high resolution, the freshwater lenses that are showing up much more clearly and much more distinctly, again, because that stable layer is being more resolved near the surface. Since it's a coupled run, we could do a few things. And in this case, Eric pulled out the vertical, the precipitation. So this is a 10-day average of precipitation, and it's averaged zonally. So the results from, again, the only changes have been the resolution of the ocean model. So the 1 meter resolution is in blue and the 5 meter resolution is in red. And you can see that there's been a shift in sort of the regions of peak precipitation, just based on the fact that you're doing a better job at the 1 meter resolving sort of the upper temperature and salinity variability. And I've stolen this from Calvin Richards. Fortunately, all these people are here at this workshop, and you can see, and they will have posters, and you know there can be a lot more discussion with them. But in this work, they're looking at the importance of really fine scale shear and the impact of dissipation on that. And you can see they're looking at the dissipation here on the upper left, and what you see when you include how much more closely that includes the fine scale shear patterns, and that they get a change in sea surface temperature by increasing their vertical resolution in an OGCM with an improved ENSO evolution and improved cold tongue characterization. So we're seeing these in the models. The question is, how much of this is real and how much of this should we be worrying about? So I'm going to talk for a few moments about 3 kinds of questions that are sort of my provocative questions for this workshop. And I'm going to ask is, if we thought of this study, you know, a new Toga core, what would it look like if we just said, instead of this ocean and this atmosphere and this interface sort of idea, what would we design if we looked at it as a coupled boundary layer system? And as part of that coupled boundary layer system, that includes not just the physical properties, but the biogeochemical properties as well, because they all interact together within the sort of the coupled boundary layer. And so it's kind of a different look than what was done in Toga Core. But if we started to look at it in this way and said, can we resolve the processes and the things that are happening sort of at the same scales in the ocean and the atmosphere, instead of thinking these as two really separate systems. So this kind of follows on what Charlotte was talking about earlier. All right, so another question for you is, what study do we get if we ask for and get real answers from the modelers? You know, what is needed? I said here the answers cannot be everything everywhere, because we would really like everything everywhere, but that's just not possible. But what measurements are really, really key for knowing how these coupled systems work together at these scales? And if what we're seeing from the modeling simulations really are representative of reality. So for instance, from the atmospheric boundary layer community, in a nice workshop that Shui Chen helped lead, you know, one of the things that was talked about is fluxes within the boundary layer are really a holy grail. We could ask, where are the model instabilities? So we could be doing a lot more work pressing in that direction. We should be asking ourselves, what kinds of data do we need to improve high resolution models, including large eddy simulation models, which might be a different type of data. In this case, we might need lots and lots of data for statistics. And we also should, at some point, need to agree on some non-tunable physics. For instance, you can't make a coupled model and tune your flux parameterization to make the atmosphere seem right. We should have this discussion. What study do we get is my third question. If we free ourselves from thinking of a process study as being built around ships and airplanes. You know, certainly since Toga Core, there are many new types of measurements that are being made, and I'm really hopeful to hear much more about these. I'm just, you know, from even now we have, you know, LiDARs on buoys now, wave gliders, sail drones, and gliders within the ocean. On the right here is nice UAVs, unmanned aerial vehicles from Chris Zappa's group, which have multiple types of payloads. They're deployed from ships. They have a drone deployed micro drifters, which do atmospheric profiles, hits the ocean and becomes a drifter. The direct calculation of turbulent fluxes within the boundary layer through eddy covariance processes. Anyway, lots of new types of observations. And so I would like to think, if we could spend a few moments during this time to say, what if we didn't envision a process study as being ships and airplanes, but something a little bit different? And when I'm thinking about that, that leads me to, and that Billy had kind of mentioned this as well, sort of what would such a site look like? So what might it look like? And as part of that, what would it, if you think about some of the things that we really concern ourselves with, what if power wasn't really as much of an issue as we often think about? What if time, so ship time, for instance, is not so much of an issue because it's, you know, we're putting out things that can sit for, you know, a longer period of time. So this is actually an idea that was brought up by folks that we've talked to in the wind energy, said, what would you design? And they picked up a structure like this was one of the designs that they came up with. Note that there's a wind turbine on it. There's solar panels on it. There's a van here that you could have all kinds of things. We could have active sensors and passive sensors. We could have a generator on this to provide power. So power is not quite as much of an issue. Putting a big tower on it would allow us to do things within the atmospheric boundary layer. And of course, there's, you know, many ways of addressing the ocean boundary layer. So this is a question, what would we think of if we thought of a system and said, let's free ourselves a little bit from the way we've done it in the past. Let's not worry quite so much about power, time. What would we do? So I don't have any conclusions, just questions that I hope to hear some thoughts about during this discussion. So what processes are most important? What scales do we need? Where would we need such a thing? What are the new ways we can get this data? And finally, to quote Bob House, we need more holism and less reductionism. Thank you.
All right, thank you, Carol Ann, for all those great questions. Before I start taking questions in the chat, I just want to say, Carol Ann showed a nice slide of observing systems. We shared yesterday a slide deck that our scientific organizing committee has put together. It's sort of a primer on what are some of the available observing systems. You can find that in the Slack channel, or we'll try to post a link to it here in the chat. But anyway, to start off with questions, we have a question from Giuseppe Torri. He's asking about your WRF-ROMS coupled simulations. He wants to know, what are the changes that you observe at the smaller scales and atmospheric convective systems when you increase the resolution of the ocean? For example, do clouds get taller, cold pools live longer, etc.? Have you looked at any of that from these simulations?
And in fact, I'm going to punt slightly on this because Eric Skillingstad has a poster, I believe, here, and he's been looking very heavily at cold pools. So I don't want to steal any of his thunder about what we're seeing there. So I'll leave that question for him.
Fair enough. So Janet Sprintal has a question for you. She says, we measure boundary layer heat fluxes by obtaining the state variables and using core-derived algorithms, and also by direct covariance flux measurements. As she understands, many models use the core, her question is, I understand many models use the core algorithm approach, ? Are models using the DCF measurements to their full advantage?
Oh, that's a really good question. I would say, first of all, a lot of models do not use the core flux parameterization, and in fact, many models use parameterizations that are demonstrably different, and so it does affect things. I didn't put in a picture here, but for instance, the ERA5, when we look at balances in the tropical Pacific at various regions, when we look at the satellite evaporation and precipitation and we balance it with the reanalysis moisture divergence, those balance quite nicely. But then when you look at the evaporation and the precipitation in the reanalyses, they're much, much higher. And some of that is partially due to the flux parameterizations that are being used. And the next question about the DCFS. So far, there has been some discussion of using the actual flux measurements themselves directly within, how would we do that sort of within a modeling capability, looking at, now we could look down at, sub-mesoscales and so forth. But so the vast majority, and I'm sure someone out there will now know this of someone who has done it better, but it's basically we're using the flux parameterizations that are derived from the flux measurements themselves.
All right. Anish has a question for you. He asked, could you comment briefly on the benefits of supersites, such as you presented, on the calibration and validation of satellites, both for atmosphere and ocean?
Oh, okay. That's an interesting question. I think one of the things that we talk about when we think about the calibration and validation of the satellites, I'm thinking, for instance, of surface radiation measurements. So it's not just that we need high quality surface radiation measurements to help out the satellite atmospheric radiation community. They very much want profiles of atmospheric boundary layer temperature and humidity. And so for them to improve their retrievals, they need not just the surface, but the boundary layer profiles. I would say, as someone who works on doing the latent and sensible heat flux from satellite, that the profiles are also kind of key. It's good to know from the in situ measurement sort of how wrong we are or where we have errors, and at the same time to actually improve the simulations and improve the retrievals. Having more information, particularly on the atmospheric boundary layer side, would be very helpful. And so, one of the things I didn't say with, some of the platforms that, that have been talked about with like a super site, you could have people stay, you could have people stay out on them, and we could be releasing radiosondes, but we could be having unmanned aerial vehicles. We could do a couple of different things thinking about it if, again, we wanted to go in that direction.